Okay, so moving on. Given a probability distribution, remember there's a big difference between looking at just a regular probability distribution and looking at a set of data that we already have in hand. And when we have data, the first thing we want to do after we accumulate something like a table, you can make a sort of comparison in your mind to these probability distributions as being sort of analogous to what we've already done with sort of building tables as frequency distributions and frequency histograms representing graphs like this. And then the first thing after we found frequency distributions and histograms is we went to find what the mean is, right? We wanted to find the measure of center of our data. Now the difference here is that we haven't actually done anything. We actually haven't, we don't have data on hand in terms of the same way at least that we did before. So in this particular case, I'm thinking about this probability experiment of drawing some sort of group of people from this town to be my jurors. And although I haven't actually done it, it's not like I have a collection of 500 or 600 juries that I'm finding out how many Mexican Americans were on each jury. I'm just literally thinking about the hypothetical, theoretical probability of these kinds of things of happening. But I can still think about what the center of my data is. So if this was a frequency histogram, where would you identify the center as? Where would the middle point of this data be? Maybe here, maybe here. What's the tipping point? I don't know, maybe about 9 or 10, or maybe I'm a little bit too far to the right. Maybe it's closer to 9. But I'd still be able to get a visual sense of where I think the center of this data is. And so what do we mean by the center of our data in terms of a probability distribution? Well, I haven't actually calculated anything, but I can still think about it in terms of a weighted mean. So what do I mean? Let's look at this table, and let's remember what we know about weighted means. Where's my table? I must have a nice table here. So I want you to think about what would the value represent if I were to take this table and I were to treat the value of the random variable here on the left, x, as my quantity, and I were to treat these probabilities on the right as weights. So what I mean is I want to take the value of 0 approximately 0 times. This is 0 plus, I didn't mention this before, but this just means that we've rounded this number off to 0. The probability of getting no Mexican Americans in this situation is extremely small, much less than 1,000th of a percent. So we just round that down to 0, even though it's technically not 0. It's just been rounded off to 0. But anyways, and I would expect to get something like 4 Mexican Americans about 0.01% of the time. So it makes sense in this case to try to use these probabilities as weights, as if I was calculating a mean. What I'm thinking is that if I actually did select 100,000 juries or 1,000 juries or something like that, out of those 1,000 juries, how many times would I expect to get 12 Mexican Americans on my jury? Well, I'd get it about 6.9% of the time. And how many times would I get 7 Mexican Americans on my jury? Oh, about 5% of the time, and so on and so on. So by treating each of the values of my random variable as the measurement, and by treating the probability as the weight, I can calculate a weighted mean. And when I find a weighted mean, you'll remember that I take the sum of the weights times the values, and I divide by the sum of the weights. And the sum of the weights in this case is always just 1, isn't it? Because if I add up all the probabilities in the probability distribution, it must add to 1, because it represents all the outcomes, so there's a 100% chance that something in my table will happen. And this value is what we call the expected value. We can think about it informally as being sort of the mean of the probability distribution. Sometimes it's in fact just called the mean. But it doesn't represent an actual mean of any concrete data that we've collected. It represents what we would expect to happen in most cases, which is why the name expected value is a little bit better, in my mind at least. And so if I have a discrete random variable, the expectation is equal to the sum of all the values of x times the mean. Now that makes it very easy to calculate. How easy is it? Well, if I wanted to find the expected value of the experiment of just rolling a die 1 time, then what do I have to do? I have to take all the values, 1, 2, 3, 4, 5, and 6, multiply them by their probabilities, that's easy enough to do, and add it all up. So to find the expected value, the way I'm thinking about this is, what will I expect to happen when I roll a die 1 time? What number should I expect to get based on the likelihood of all these outcomes. I multiply 1 times 0.6, 2 times 1 over 6, 3 times 1 over 6, 4 times 1 over 6, 5 times 1 over 6, and 6 times 1 over 6. And if you carry out this multiplication and add up all these numbers, you'll get exactly 3.5. And so, what does that mean? Why does that make sense? Well, all it means is that sort of the center of this data is about 3.5. And if I look at the graph, that's exactly right, right? This is the middle of this. If this was a histogram, 3.5 would definitely be the mean of this. It's the exact middle point, right? Notice that it's not one of the possible outcomes either. I can't roll a 3.5 when I roll a die. That's not what this value is meant to represent. It just represents the number that we expect to get. If I get a 3.5, if I get a number around 3.5 when I roll a die, I don't expect that anything atypical has happened. That's what we mean by expected value. It's the expected number that we might get when we carry out a probability experiment. So, find the expected value of this probability experiment and try to think of an English sentence of how to interpret it. What's the expected number of Mexican-American jurors in a town that is 80% Mexican-American? Try to answer this question, and I'll tell you the answer in just 1 second. Okay, so did you get it? Well, it's pretty simple. All you have to really do, like I said, is take each of these values of x and multiply them with the corresponding probabilities, and then add them all up. So that's what I did. I skipped the first 4 columns because 0 times 0 is 0, 1 times 0 is 0. The first 4 columns, of course, when I calculate x times p of x, it's just 0, 0, 0, 0. And I don't have much space trying to write with this stylus, which I'm not very good at. I started at 4, I multiplied 4 times 0.001, this is x p of x here, and I got 0.004, and all the way down to multiplying 12, I multiplied the value 12 jurors. How many times will that happen? Well, that happens 0.69% of the time, 6.9%, excuse me, so that gives me a value of 0.828. And when I add all these up, I calculate x times p of x, I get about 9.6. And the beautiful thing about mathematics is usually that you know you're right, you've done something correct, if it really makes sense when you look at it. And so what this should tell me is that in this particular town, I should expect on average to get about 9.6 jurors out of 12 that are Mexican American. And, you know, looking back, first of all, it makes sense to think the town's 80% Mexican American. That seems like a reasonable number of jurors to expect. And looking back at our probability distribution that's displayed as a graph, it definitely makes sense to think that 9.6 is sort of the center of this set of data. It's the expected value. What is the center of this data? We said it was around 9 or 10, and so 9.6 sort of hits the nail right on the head. This is how we find the expected value of any probability distribution. We take the value of the random variable x, we multiply by the probability, and we add it all up. Okay, and so if we think about the expected value as roughly the mean, or approximately the mean, or the mean of our probability distribution, then of course once we have a data set, or some sort of distribution at least, and we have a mean, we can go ahead and consider the standard deviation. How spread out is this probability distribution? Of course, we've already seen 2 examples which should have vastly different sort of standard deviations. We have our distribution of data here that's very uniformly spread out, and so we would expect this to have a certain type of standard deviation. And then we have our jury distribution, which looks a lot more like a bell curve, like a normal distribution. And so it still makes sense for us to consider things like the standard deviation of a probability distribution. And so how do we find that? Well, we actually find it in the exact same way that we used to find standard deviation. The only difference now is that instead of calculating, we'll use our formula for estimating standard deviation based on a frequency distribution, and the only difference is now that we're using probability distribution, we're going to treat the probability of x as if it were the frequency. So again, the assumption here is something to the effect of saying, well, in a probability distribution, I'm assuming that if this experiment was conducted 10,000 times, then the probabilities would represent something like the frequency, right? At least the data would be in proportion in that sense. If it was a 50% probability of getting this value, then I would expect, out of 1,000 times to get it 500 times or whatnot. So to find the standard deviation of a discrete random variable, what do? Quite simply, we just find our standard deviation formula in the same way that we did. And if you remember the formula for estimating standard deviation from a frequency distribution, we would take it as the sum of all the values x minus the mean. So we can do the same thing here. We just take x minus the expected value. Then we square it, we multiply it by the frequency, that's right. And in this case, we're going to treat the frequency as the probability of x. So what does this formula say? I divide it, and then I divide by the probability of x is all squared, but of course that just comes out to 1. So what does this formula say? To find the standard deviation of a probability distribution, I take every value x, I subtract the expected value, I square it, I times it by its probability, and then I take the square root. So one quick example, finding mean and standard deviation. I've got a probability distribution off to the left, and what this represents is the likelihood of getting each of these different categories of hurricanes. How ironic, right? A hurricane question for us in the Virgin Islands. And so what I have here is this probability distribution, and the random variable is associating to each of the values x, which represent the category of a hurricane that could come by and theoretically hit us, to the probability of getting such a category hurricane. So the likelihood of getting a category 1 hurricane is about 39%, meaning 39% of all hurricanes tend to be category 1, 26% category 2, 27% category 3, 6% category 4, and only 1% chance of getting category 5. So fun application question, what's the probability of getting hit by 2 category 5 hurricanes within 2 weeks? We can figure that out. Doesn't matter the probability, it happened, right? And of course, this is U.S. mainland categories. U.S. mainland, so the probabilities could change slightly and would probably change if we considered the Caribbean instead. Anyways, what I want you to do is take this probability distribution to the left, and I want you to find its mean and then find its standard deviation and see if you can tell me what those are. So, did you find it? The mean is pretty straightforward. All I have to do is take each of these values, the probabilities, and multiply them by the value of x. And don't forget that if I were to put this in our table form, don't be only able to do things when you see it in a familiar form. Understand the ideas. Then this table would just look like this, right? For each possible value of x, that means for each value of category hurricane, I would be able to associate it to these different probabilities. So to find the expectation, the expected value, or the mean, all I do is multiply these values of x times their probabilities and sum them up. And when I do that, I get 1 times 0.392, 2 times 0.265, etc., 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 and I get approximately 2.04, which, because we're talking category hurricanes, it doesn't really make sense to keep all these decimal places of accuracy. If I say, oh, somebody asks you what category hurricane's coming, you don't say, oh, a 2.04 is coming. That's just, it's irrelevant and confusing. So we'll refer to it as saying the expectation in this case is about 2. Our interpretation is that of the hurricanes, that if a hurricane is to hit the U.S. mainland, our expectation of its severity is approximately category 2. And so now can you find the standard deviation? Assuming, let's round off and let's keep our expectation at 2. Especially because, we have to do some calculations. Assuming that the expectation is 2, go ahead and try to find the standard deviation of this using the formula we just talked about. Remember, what that means is I take the value of my random variable x, I subtract 2, I square it, multiply it by the probability, add it all up, and take the square root. So give it a shot and see if you can get the right answer. So I go through step by step here. You can double check. I take my expectation of 2 and I subtract it at each point from the value of x. So I start with when x is 1, 1 minus 2 is minus 1, 2 minus 2 is 0, 5 minus 2 is 3, and so on and so on. To each of these values I square it, x minus the mean squared, minus 1 becomes 1, 0, 1, 4, 9. Multiply by the corresponding probabilities. So I take 1 times 0.392, it gives me 0.392, 0 times 0.265, gives me 0. I'm multiplying these two columns here. Then I add it all up. I get 1.06, and I take the square root, which is approximately 1. So what that tells me is that the standard deviation of this set here is 1. I have a mean of 2 and a standard deviation of approximately 1. And that gives me a sense of the spread of the data. And I can do this for any probability distribution. I can find the mean and the standard deviation.